right. Morning, everybody. Good morning, everybody. Welcome to video 2 of floor 9.5. In this video, we're going to be talking about rotations. In our first video, we wrote balance factor of and is balanced from. At this point, the tree can now report how lopsided it actually is. Self-test balance phases 1 through 3 are green. Balance correctly calls McCown's catalog not balanced. Phases 4 and 5 still fail. Those need rotations, which is going to be handled today. Now, in today's video, we're really going to be working with two short functions in our hero/BST header file. We have rotateRight and rotateLeft. Each is 4 lines of pointer surgery that's happening here. The lesson really today is not the 4 lines, it's why the move is safe. A rotation changes a subtree's height, but leaves its in order exactly as it was. That is the whole reason you're allowed to do it to search a tree. Now, let's really, from the last video, we taught the tree to see its own lean and all those things. So, to get started, we're going to write these rotations, but first of all, I want us to kind of think a little bit about how we'll do this. So I'm going to pull us up a notepad ++ file, and we'll get to work there first. Okay, here we are. So let's draw us a little stick here. So let's say we had 1 at the top, and then we had 2, and then we had 3. Let's say it was like that. So essentially, it's just a lopsided to the right. Okay. Now, so we have 1, then 2 to its right, then 3 to its right. So this is what we call a stick. Okay. Now, its in order walk is left, node, right, all the way down. In this way is 1, 2, 3. Okay. Now, that order is going to be really important for when we manipulate this thing. Okay. Because this the order is really sacred in this case. It has to be the same no matter what we end up doing to it. Okay. So the move here. A left rotation at 1 says, my right child 2 is doing too much work holding up this tower. Let 2 come up and be the new top, and I'll hang underneath it to the left. So that's what a left rotation would be. Okay. So if that's true, 2 rises to the root. 1 drops to become 2's left child, and 3, which was already to the right of 2, stays 2's right child. So that's what we're saying right there. Okay. So then that means this tree becomes as such. So we have 1, then 2 at the root, and then 3. So the in order walk is the same, right? It's identical. The shape went from 3 levels to 2. It's shorter, faster, but the order didn't budge. That's the magic, though it's not really magic. A rotation only ever rehangs a subtree onto a node that's already on the correct side of it in value. Now, there is one more wrinkle in the general case. If 2 had a left child of its own, that subtree would have to swing over to become 1's new right child. Okay. Our stick has nothing there, so, in this example, not a big deal, but it is an important wrinkle to understand. Okay. So let's get in here and let's fill in this rotate right. So what you do is to get us a pivot. So we'll get us a pointer pivot here. We'll point to the left of n, and then we'll say n of left equals pivot to the right. Okay, and then we'll say pivot right is equal to in, return our pivot. Okay. Now, this we're going to write this right. We wrote this right rotation here first, a mirror of what we drew for a left-leaning tree here. Okay. Now, if you see here, I have a little ASCII tree here. So this is important. Just kind of look at this as we go. The pivot is n's left child in this case. That's the one coming up. N's new left becomes the pivot's old right subtree. That's the orphan swinging over. The pivot's right, notice there, becomes in, right there. The old root, in that case, is folding down. Okay, so then you return the pivot. It's the new top of this subtree, and the caller relinks to it. Exactly like insert and remove return their new subtree roots in last module. So that's 4 lines. The hard part really was the picture, but we kind of already drew that and understood. So see kind of how we're at now with in, right? So pivot is n's left child. Okay, so that's going to be our orphan swinging over. So you notice as we shift the pivot up, okay, A still stays to the left right here. But then you see that this pivots down, of course. And then pivots right here. You'll notice we'll slide it over here next to N's left. And then C is still to the right. So pretty cool. Okay, so that's our code right there for that. Now for our left rotation, what we need to do here is we're going to say node gets a pivot. This will be on n of right. We'll say n of right is equal to pivot left. Pivot left is equal to n, return pivot. There we go. So rotation left is just rotate right with every left and right swapped. It's the exact move we drew on the board for the 1, 2, 3 stick in Notepad++ a second ago. Pivot is n's right child. It comes up. N's new right is the pivot's old left subtree. The pivot's left becomes n. Return the pivot. If you can't remember which is which, a left rotation fixes a right heavy tree. It pulls the tall right side up and over to the left. The name is the direction the old root moves, not the side that was heavy. Okay. So let's go ahead and build this here real quick. Make sure everything's all good in the neighborhood. Should be good. And then we'll self-test balance. And now we've got our rotate root left is working good. Okay. So phase 4 is now green. Read what it checked here because it's exactly kind of what we just talked about on Notepad. Rotate left on the stick. 1, 2, 3 produced 2 at the root at height 1. So 1 level shorter and the in order walk was unchanged. That order kept clause is the assertion that matters. A rotation that shortened the tree but scrambled the order would be worthless and the test would catch it. So phase 5 still fails. We can rotate now, but nothing yet decides when and which way to rotate. That decision will be saved for video 3 and the final payoff for this floor. Anyways, I hope this was a helpful video, and I will see you in the next one, and we'll wrap up floor 9.5. Bye-bye now.